Hello, in this video we'll be discussing the basics of the quantum mechanic model of the atom. So up until now you've primarily been dealing with the Bohr model of the atom, which says that the atom is similar to a solar system, where you have a nucleus in the center, which is then orbited in fixed circular orbitals, the electrons. So the electrons are in those fixed orbitals surrounding a central nucleus. Well, eventually, in the early and to mid part of the 20th century, several physicists and chemists discovered that the atom actually doesn't really behave that way, and that the atom is actually a lot more complicated and it has its own set of physics known as quantum physics. And ultimately, they discovered that electrons, instead of existing in those circular fixed orbitals, actually exist more in regions around the atom, around the nucleus. So that's why sometimes you'll hear it referred to as the electron cloud model, and that's because we think of the electrons as being more densely associated based on specific regions around the nucleus, based on energy levels, rather than in specific circular orbitals. So that's why sometimes you'll see it referred to as the electron cloud model. Now there are three main principles that you'll need to know in relation to quantum mechanics. The first one that we're going to talk about today is the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle states that we cannot know both the location and momentum of an electron at the same time. We can know one and we can know the other, but we cannot know them both at the same time. If we know the momentum of an electron, we cannot know its location. If we know where the electron is, then we cannot know its momentum. That's one of the key principles of quantum mechanics. Another key concept of quantum mechanics is the idea of particle-wave duality. So electrons exist as both waves and particles simultaneously. This is something you talked about a little bit with light, because light also shares the same property. Light can exist as both waves and particles, same thing with electrons. So we're kind of moving away from thinking of electrons as those little dots of the Bohr model, and we're starting to think of them more as waves of energy. And the electron locations, like we said, instead of those fixed circular orbitals of the Bohr model, we're thinking of the electron locations based on probability. And there's going to be a region of probability where certain electrons exist at certain energy levels. So that's going to be where we get our shapes of our orbitals from, based on the probability of an electron being within that general space at any given time. And these orbitals have specific identifiers. We have the s orbitals, the p orbitals, the d orbitals, and the f orbitals. And that's how you're going to see them referred to when it comes to electron configuration and with identifying quantum numbers. Also, electrons are going to be paired. So it's going to be similar to a positive and a negative, kinda. So kind of like you have a north pole and a south pole on a magnet. Same thing with electrons. Some electrons are going to be upspun, some electrons are going to be downspun, and they're going to be paired together. And when they're paired together, that's how they fit into these suborbitals within the orbitals themselves. So let's talk a little bit about the shapes of these specific orbitals. So like I said, we have s orbitals, we have p orbitals, we have d, and we have f. And they each have unique shapes associated with them. These shapes, you can kind of think of the shapes of these orbitals as like the houses. So this is the house where the electrons live, and it has a defined shape. Just like your house or your dorm or your apartment has a specific shape. Same thing with these orbitals. Let's take the s orbital, for example. The s orbital has a spherical shape. And the reason it's a spherical shape is because in this region, so if you picture, for example, let's say the nucleus is in the middle here. So let's say we have a nucleus here in the middle. This spherical shape says that the electron is sort of bouncing around this orbital. It can be anywhere. Any of these dots that I'm putting down could be where the electron is. We don't know, though. But because the electron is bouncing around that general area, we call that the orbital. And that's why it's shaped like that spherical shape. And the shapes of these other orbitals come from a similar property, where those are just the areas where the electrons generally can be found. But they're never in one specific spot at all times. They're always mobile, they're always moving around. So for the s orbital, it can hold a total of 2 electrons. So 2 electrons can fit inside the s orbital. And the s orbital is associated with these 2 columns here that I've highlighted in purple. So column 1 and column 2. And each energy level has 1 s orbital. So energy levels increase as you go down the periodic table. So up here we have energy level 1, where n equals 1, and down here we have energy level 7, where n equals 7. And there's 1 s orbital for each new row of the periodic table. So for example, hydrogen would be 1s. Lithium would be 2s. Sodium would be 3s, and so on. So that's how you can start assigning these energy levels. Then we have the p orbitals, and they come from this area of the periodic table that I've highlighted in green. And you'll notice there's 1, 2, 3, 4, 5, 6 elements in each row of the p block. And that's where these 6 electrons come from. So the p orbitals can hold a total of 6 electrons. And they start at row 2, where n equals 2, and they go down to n equals 7. So they start at 2 and they go down to 7. So there's 1 p orbital for each new row from 2 to 7. Then we have the d block, or the d orbitals. And they're going to come from this middle part of the periodic table here, where we have the transition metals. And they can hold a total of 10 electrons. And this is where things start to get a little weird. You would think, because this first row of the d block is in row 4, that it would be 4d. But in reality, this is 3d. So the d block starts with 3, then goes to 4, then goes to 5, then goes to 6. So the d orbital actually its energy levels are slightly different to the s and to the p. And that's something we'll see come up when we talk about electron configuration, for example. So the d goes from 3 at the top down to 6 at the bottom. So its trend is not similar to s and p. And its orbitals start to look a little weird. Here's just an example of 3 of the orbitals that you have for the d. In total, you have 5. But this is just a picture of what some of them look like. And then we have the f orbitals. And remember, the f block is down here. And remember that the f block actually goes right here where I put these 2 stars. So in reality, the periodic table is longer than you usually see it. But there's 14 elements going across here. So starting from here and going across, there's 14 in each row, which means that the f blocks, the f orbitals, can hold up to 14 electrons. And similar to the d block, even though the f rows are in rows 6 and 7 of the periodic table, their energy levels are 4 and 5. So the first row here would be n equals, well, not n equals, but the energy level 4. And down here would be the energy level 5 for this row. But we'll get into energy levels and orbitals when we talk about quantum numbers. But just know that d and f don't follow the same pattern as s and p. D starts at 3, so that kind of rhymes. You can kind of put it that way. D starts at 3, and F starts at 4. So F, 4, those kind of sound similar. D and 3, those sound similar. Maybe that's a good way to remember where these start, which will be helpful when you start doing electron configuration. So D starts at 3, F starts at 4. And that's sort of an overview of quantum mechanic basics. In the next video, we'll discuss how to identify quantum numbers and how to write them for individual elements.